A very good day to you, gentlemen and ladies. Thanks for stopping by this video. So today we are going to learn about Kepler's laws of planetary motions. What this simply means is that when planets, when they revolve around their stars, there are some laws that govern them. And there are about 3 of those laws that were invented by Mr. Kepler. All right, so we're going to go through all 3 of those laws today. The first law is the law of ellipses. This simply states that when planets revolve around their stars, they do so in an elliptical shape, which means in the shape of an ellipse, not in a circular shape. Planets do not go around their stars in a perfect circle. No, they do so in an elliptical orbit or an elliptical shape, which means the shape of an ellipse. That is the first law. The second law is the law of equal areas, and this simply states that as a planet revolves around their stars, the distance or the area they cover from one point to another point drawn towards the stars will be equal. In this case, S1 will be equal to S2, which means the area of that triangle in S1 will be equal to the area around S2. We'll dive a little deeper into that as we proceed. And the third law is the law of periods, and this simply states that the amount of time or the period it takes a planet to go around the star completely for one revolution will be directly proportional to the distance of the planet from the star. In other words, the amount of period it takes, the amount of time it takes is directly proportional to how far the planet is from the star. We will dive a little bit deeper into that as well. So let's go deeper into the first law, the law of ellipses. When planets orbit the sun, they do so in ellipses with the sun at one of the foci. What this simply means is if you were to construct an ellipse, you would need 2 focus. All right. So we call the plural form of 2 focuses, we call them foci. All right, F-O-C-I. So which means as a planet revolves around their star, the star cannot be in the 2 focus at the same time. The star can only be in one foci or one of those foci at a time. So looking at this diagram again, the sun can only be in one position. The sun cannot be in the other foci at the same time. So as a planet revolves around the star, it does so in an elliptical shape. That means that the planet would get really close to the star at certain points, and then at other points it will be very far away from the star. So when the planet is very close to the star, that's the period you call the perihelion. From the word perimeter, for example, which means close by, nearby, just around the corner, and the word helion, which means the sun. When we talked about heliocentric, and the sun fuses hydrogen into helium, so that's where that word came from, helion, so which means close to the sun. So perihelion simply means close to the sun, while aphelion means far away from the sun. So that is one way to interpret the first law. So let's look at some questions, regent questions that can cement or help us cement in that concept. Let's look at question 1 here. Question 1 says, which object is located at one of the foci of the elliptical orbit of Mars? So Mars goes around the sun in an elliptical shape. So what object is in one of the foci? Of course, it's going to be the Earth. It's going to be the sun in one of the foci. So our correct answer here would be the sun. It cannot be Earth. That would be geocentrism. It cannot be Betelgeuse or Jupiter as well, because Earth and Jupiter are planets. So it cannot be Betelgeuse because Betelgeuse is not the name of our star in our solar system. It's the star of our solar system that would be at one of the foci of Mars. Let's look at question number 2 here. Question number 2 here says, describe the change that takes place in the apparent size of the sun as viewed from Earth as Earth moves around from the perihelion close to the sun to the aphelion far away from the sun. So as Earth moves from the perihelion, which is the point where it's very close to the sun, everybody viewing the sun will look bigger because Earth is closer to the sun. So the sun is going to look bigger at the perihelion, and when the Earth continues to revolve all the way back to the aphelion, because the Earth is far away from the sun now, the sun is going to look a little bit smaller. So that is how it's going to affect the size of the Earth when viewed from Earth. So at perihelion, the sun will appear bigger. At aphelion, the sun will appear smaller. That is the first law of planetary motion. So let's dive into the second law, the law of equal areas. This means that a planet will cover equal areas in equal time. What that means is, as a planet moves from point A to point B, the amount of time it takes to move from point A to point B will be the same time it takes to move from point C to point D. In that way, the shaded area that you see in this picture will be equal to one another. So the shaded area here will be equal to the area of this area of this shape as well. So what that simply means is it's going to take the same time from A to B and then from C to D. Even though C to D is a longer distance, the planet is going to cover it in the same time by speeding up. So the planet will speed up to cover that longer distance when it's much closer to the sun, which is during the perihelion. The reason for that is, as a planet gets closer to their star, the gravitational pull of the star on the planet gets greater. All right. Two objects in space, the closer they are, the more powerful the gravitational force between them. So because the gravitational pull is stronger here, the planet will increase in its speed, in its velocity, as it moves from point C to point D. Contrary, at the aphelion, because the planet is very far from the star now, the gravitational pull is very weak because the planet is farther from the star. So the planet would move very slowly around the aphelion. Okay, so this guy here would kind of put it in perspective. As the Earth revolves, it speeds up when it's around the perihelion, and then when it's around the aphelion, it slows down, and then it gets faster and faster, and then speeds up, and then when it gets to the aphelion, it slows, and then when it gets to the perihelion, it moves faster. So that is how the planet does it. So in that way, the amount of area covered from point C to point D will be the same thing as the amount of area covered from point A to point B. That is the second law. Let's look at some regent question on that second law and cement it in. So let's look at question number 3 here. All right. Question number 3 here says, if the shaded portion of the orbital plane are equal in area, the time period it takes to move from points P1 to point P2 will be equal to the time period between. So we're looking at the amount of time it takes to move from point P1 all the way to point P2. So the amount of time it takes, again, will be equal to any other 2 points. For example, the amount of time it takes to move from point 1 to point 2 here will be the same amount of time to move from point 3 to point 4. So we're going to look at that option. Point 3 to point 4 is right here as option B. So that's going to be our correct option. Note, it's not from point 2 to point 3. Point 2 to point 3 is not amongst the shaded area. Remember, it is the shaded area that are equal. The shaded area that are equal. All right, so P2 to P3 is a different part, or is a much longer part. It's not going to take the same time. Rather, you look at the shaded area, the shaded portion. Okay, hopefully that helps. Let's move on to one more question. Question number 4 right here. State the relationship between Earth's distance from the sun and the Earth's orbital velocity, which means the speed at which the Earth is moving when it's closer to the sun and when it's farther from the sun, which is the perihelion and the aphelion. So when the Earth is closer to the sun during the perihelion, the Earth will move faster around this area. when the Earth is farther away from the Sun, the orbital velocity would reduce in the aphelion. So that is how you'd answer that question. All right, the orbital velocity of the Earth is faster during the perihelion and then slower during the aphelion. All right, so let's dive into the final law, which is law number 3, which is the law of periods. And this law simply states that the amount of time it takes to complete one revolution will be directly proportional to the distance, the average distance of the planet from the star. Simply put, the farther the planet is from the star, the longer the period of revolution for that star. The next slide, we nail that in. So when you look at the white planet here and the green planet, because the green planet is farther away from the star, the green planet will take a longer time to complete one revolution compared to the smaller guy, the white planet that is closer to the sun. Because it's closer to the star, it has a shorter distance to cover. Because it has a shorter distance, it's going to move quickly and cover one revolution much more quickly. Simply put, a planet like Jupiter that is far away from the sun will have a longer period of revolution compared to a planet like Mercury, which is the closest to the sun, to complete one revolution. That is just what the third law simply states. Let's apply that to some regent question here. Let's look at question number 5. All right, question number 5 here says, compared to planet A, planet B has, so we see planet A is closer to the star and planet B is farther away. So compared to planet A, planet B has a weaker gravitational force to the star and a shorter period of revolution. Weaker gravitational force, yeah, because it's farther away, but a shorter revolution, no. Planet B will have a longer revolution around the star. So planet B is going to have a longer revolution. So it's definitely not option A. Option number B says a weaker gravitational attraction to the star and a longer period of revolution. That looks like my answer. A stronger gravitational attraction, no. Planet A will have a stronger gravitational attraction than B. D is stronger, no. So D is out of the way and C is out of the way. Our correct option is B, a weaker gravitational attraction because it's farther away, and then a longer period of revolution because it's farther away. Last question here. Which characteristic is directly related to a planet's average distance from the sun?